In this informational video, we will show a strategy for diagnosing a failure in the HVIL circuit. HVIL stands for Hazardous Voltage Interlock Loop. While the method shown may not cover all vehicles and variants, you can use the general idea to develop your own strategy to best locate a failure in the HVIL circuit for the vehicle you're diagnosing. The HVIL is a safety feature used in high voltage systems, and its purpose is to protect from electrical arcs and unintended contact with energized components during the assembly, repair, maintenance, and operation of a vehicle. In the ISO International Standard, ISO 6469-3, 2001, Electric Road Vehicles Safety Specifications Part 3, Protection of Persons Against Electric Hazards. It is stipulated that the high voltage components on the electric vehicle or hybrid vehicle shall have a high voltage interlock device. The following components are part of the traction voltage system or TVS. All traction batteries, high voltage wire harnesses and connectors, DC to DC converter, electric motor drive, EMD, electric motor, EM, battery thermal management system, BTMS, traction voltage junction box, TVJB, traction voltage monitoring unit, TVMU, charging switch unit, CSU, electric vehicle air compressor, EVAC. The HVIL uses a continuous low-voltage loop that monitors all high-voltage connectors and components in an electric or hybrid vehicle. Every connector or lid containing live traction voltage is equipped with a connection that monitors the system's integrity. If the circuit is open, for example, if a component lid is removed or traction voltage connectors are disconnected, the Energy Storage System, or ESS, disconnects immediately by opening the TVS contactors. The contactors are located in the ESS contactor box. How does HVIL work? When an HVIL fault is detected, such as a damaged connector, a damaged wire, or an internal component failure, a diagnostic trouble code, DTC, is triggered, and an alert appears in the vehicle's instrument cluster and informs the driver that there is a fault in the vehicle and it needs to stop for service, since the operation of the vehicle may be limited. There are two different HVIL loops, Loop A and Loop C, which are physically wired to the Traction Voltage Monitoring Unit, TVMU, and DTCs are reported by the Hybrid Powertrain Control Unit, HPCU, when a fault, open or short, is detected in the HVIL circuit. When a fault is detected in the HVIL for either loop, the entire TV system is disabled by opening the TVS contactors. In this demo, we will simulate an active open circuit fault on Loop A and demonstrate how to locate the fault strategically and efficiently. The HVIL loop is a simple circuit, but because so many components are involved, deciding where to start fault tracing can be overwhelming. By observing the wiring schematic and the components on the vehicle, we determined that we could split the HVIL loop A low voltage circuit into 3 sections. Therefore, the strategy demonstrated in this video will narrow down the location of a fault by selecting easy-to-access components first to isolate the fault area. Once the fault area has been found, we can work backward to find the exact location of the root cause. Our first measurement will be from ESS1 to ESS4, thereby testing 11 out of 14 components. This can be accomplished by only disconnecting 2 connectors and not removing any parts. If this test passes, we will have eliminated 11 possible root causes, and only the remaining 3 components and 2 sections of the harness will need to be tested. However, in this scenario, the first test will fail, determining there is a fault in the middle section of the HVIL circuit. We will work backward and visually check each low voltage connector, measure the resistance of each component internally, and then perform a resistance measurement on the harness from each component we are on back to the ESS1. Step 1. Connect Tech Tool to the vehicle with an active fault code P10C6-13. This tab shows the schematics. This tab shows the special tools. This tab shows the impact links. Always refer to the tech tool for measurement details, component locations, specifications, and schematic relevant to the vehicle being diagnosed. Use the following steps for each low voltage connector check. View the schematic to identify relevant pins to check. Check that the connectors are properly connected and locked into position. Then disconnect and check the component connector. Next, inspect pins and terminals for oxidation or corrosion and ensure that they are locked into the connectors and not pushed back out of their sockets. Check that the pins and terminals are not damaged, which can cause poor connection. Step 2. Using the relevant breakout harness and a multimeter, disconnect ESS1 G22 connector B. Measure the HVIL internal resistance of the component. Check that the component has resistance. Anything greater than 500 k ohms is considered an open circuit. Step 3. Perform a connector check on the low voltage connector ESS4 G22D. Connector B. Measure the HVIL internal resistance. The component should have resistance. Measure the HVIL low voltage circuit in the wiring harness from ESS1 G22 connector B to ESS4 G22D connector B. Check the circuit has resistance. If the resistance measurement passes, then we would eliminate an open in the middle of the HVIL loop, and the next step would be to check the remaining sections of the circuit. However, this test failed in this demonstration, and there is a fault in the middle section of the HVIL circuit. So we will continue checking this circuit. Step 4. Perform a connector check on the low voltage connector, ESS3 G22C, connector B. Measure the HVIL internal resistance. The component should have resistance. Measure the HVIL low voltage circuit in the wiring harness from ESS1 G22 connector B to ESS3 G22C connector B. Check that the circuit has resistance. Step 5. Perform a connector check on the low voltage connector ESS5 G22E connector B. Measure the HVIL internal resistance. The component should have resistance. Anything greater than 500 k ohms is considered an open circuit. Measure the HVIL low voltage circuit in the wiring harness from ESS1 G22 connector B to ESS5 G22E connector B. Check that the circuit has resistance. Step 6. Perform a connector check on the low voltage connector ESS6 G22F connector B. Measure the HVIL circuit internal resistance. Check that the component has resistance. Measure the HVIL low voltage circuit in the wiring harness from ESS1 G22 connector B to ESS6 G22F connector B. Check that the circuit has resistance. Step 7. Perform a connector check on the low voltage connector A900 BTMS connector A. Measure the HVIL circuit internal resistance. Check that the component has resistance. Measure the HVIL low voltage circuit in the wiring harness from ESS1 G22 connector B to A900 BTMS connector A. Check that the circuit has resistance. Step 8. Perform a connector check on the low voltage connector U48B EMD2 connector B. Measure the HVIL circuit internal resistance and check that the component has resistance. Measure the HVIL low voltage circuit in the wiring harness from ESS1 G22 connector B to U48B EMD2 connector B. Check that the circuit has resistance. Step 9. Perform a connector check on the low voltage connector U48A EMD1 connector B. Measure the HVIL circuit internal resistance and check that the component has resistance. Measure the HVIL low voltage circuit in the wiring harness from ESS1 G22 connector B to U48A EMD1 connector B. Check that the circuit has resistance. Step 10. Perform a connector check on the low voltage connector X243B TVJ B2. Measure the HVIL circuit internal resistance and check that the component has resistance. Measure the HVIL low voltage circuit in the wiring harness from ESS1 G22 connector B to X243B TVJ B2. Check that the circuit has resistance. Step 11. Perform a connector check on the low voltage connector M121 EVAC connector A. Measure the HVIL circuit internal resistance and check that the component has resistance. In this scenario, the internal component measurement is greater than 500,000 ohms and considered an open circuit. Decommission the vehicle and check the HVIL high voltage connector pins for damage. If the high voltage connector pins are okay, then there is an internal open in the component. Conclusion. This informational video showed a strategy for diagnosing a failure in the HVIL circuit. While the methods shown may not cover all vehicles and variants, you can use the general idea to develop your own strategy to best locate a failure in the HVIL circuit for the vehicle you're diagnosing. In this demonstration, the methodology we used was to find a measurement that could be done by removing as few parts as possible and cover a large portion of components in the HVIL circuit. By observing the wiring schematic and the components on the vehicle, we have determined that we can split the HVIL loop A low voltage circuit into 3 sections. In the first measurement, we measured from ESS1 to ESS4, thereby testing 11 out of the 14 components. This was accomplished by only disconnecting 2 connectors and no parts were removed. Had this first test passed, we would have eliminated 11 possible root causes, and only the remaining 3 components and 2 sections of the harness would need to be tested. In this scenario, the first test failed, determining there was a fault in the middle section of the HVIL circuit. Then we needed to work backward and visually check each low voltage connector, measure the resistance of each component internally, and then perform a resistance measurement on the harness from each component we were on, back to the first component, ESS1. We worked methodically backward, following the schematic and performing a test at each component until we found the fault.